So, all the lectures that you have seen so far have focused on simulation based verification techniques and the general architecture of verifying design under test using simulation. So, the remainder part of the course will talk about formal methods for design verification. So, we are going to now think of ways of verifying the design without simulating it, or at least using a combination of simulation and mathematical techniques to verify the correctness of the design. The first challenge in doing things formally is to come up with a representation of the design which is amenable for formal analysis. Now, every symbolic representation of the circuit is a formal representation. So, when I say that I have a Verilog RTL for the design, that is also a formal specification of the design. If I have a gate level netlist, it is also a formal specification of the design. But then what do we mean by a formal analysis of the design? Now, the implementation is specified in that form, the specification has also to be specified formally, in the sense that the what I want to verify will have to be specified formally. When you look at simulation, the design under test, whether it is in RTL or gate level or transistor level, that is formally given. But what we want to check, that was not formally given, in the sense that before assertions came, what is the golden output, there was no formal way of saying that what exactly characterizes a golden output, right. So, that is where the formal part is missing. Then assertions got introduced. So, assertions specify certain properties in a formal way. It says exactly what we mean by the correctness of the property. But then when we are doing simulation, we are only exercising one path of the design, we are not exercising all paths. So, unless we have exhaustively tested all paths of the design, we cannot say whether that property holds on the design or not, right. So, when we talk about formal analysis, there are two aspects here. First is that the design intent has to be specified formally, and the second thing is that the design intent has to be checked on the design exhaustively. These are the two requirements of formal verification, right. Now, formal verification is not only property verification, but it is a kind of verification where the intent is specified mathematically, the design is specified in a symbolic way, and we try to match the two using a technique which is exhaustive, right. So, first, in the first few lectures of this part of the course, we will focus on what are the good ways to represent the design and the design intent, so that this matching becomes easier, right. And one of the techniques that people use here is called the use of binary decision diagrams, or BDDs. Okay. The other thing that we are going to look at somewhere down the line is SAT. So, SAT and BDDs are the two main enabling technologies for formal verification, and then we will see that how these techniques can be used to solve a variety of verification problems, from property verification to equivalence checking and things like that. Okay. So, binary decision diagrams will be referred to as BDDs in short. Okay, that is the term which is used in the verification community. We are going to first take a quick look at the motivation for decision diagrams, then we will look at BDDs, then we are going to look at ROBDDs, the reduced ordered BDDs, which actually is the BDDs that we normally use. I mean, people use, by BDDs people refer to ROBDDs only. Then we are going to study the effect of variable ordering on the performance of BDD based analysis. Then we are going to look at BDD operations. Then we will see how state machines can be encoded in BDDs, and then finally we will see how we can use BDDs to perform reachability analysis in state machines. So let us look at the first problem, that we have two logic circuits. Okay. So there are two circuits shown here, and we want to compare the two logic circuits and determine whether they are actually identical, whether functionally they are the same or not. Obviously in implementation they are different, because we have two AND gates here, one OR gate here. Here we are doing it with only one OR gate and one AND gate, right. So these two are obviously not the same design, but is the function O1 and the function O2 the same? How do we do this comparison? Now one option would be that you compute the truth table of this, and then match it. But then we know that if you have a n variable function, then the truth table of that is of the order of 2 to the power of n, right. So it is going to have order of 2 to the power of n rows. Now that can be a huge number, and that is not a very intelligent way of computing the equivalence between the two circuits, right. So this one actually talks about that you could actually do a combinatorial search to find out whether they are equivalent. In other words, you take all different kinds of input scenarios, like say for example you assign C to 0 and then see whether these two differ. So what I have done is I have taken the two circuits, connected their output through a XOR gate, and then if the XOR gate output is ever 1, then I say that these two functions are not the same, right. So when I drive C equal to 0, I find that this one evaluates to 0. So we know that when C is 0, then these two circuits are the same. So my search now should be confined to those cases where C is 1, right, because for C equal to 0 case we have already proved that these two circuits are behaving identically. So then we focus on this side. So we set C equal to 1, but if we set C equal to 1, we cannot get the values of O2 and O1 right now, right. So we need to determine the choose values of the other variables. So suppose we say that if A is 1, but then if A and C are both 1, then we find that again the difference is 0. So we discard this path of the search and say that if you take this path when A is when C is 1 and A is 1, then there is no hope of finding a difference between the two circuits. So we look at C is 1 and A is 0. So when C is 1 and A is 0, again we are unable to determine the values of O1 and O2. So we now take the value of B, and then if B is also 0, we see that the difference is again 0. So we discard this path, and then there is only one more path left, that is C is 1, A is 0 and B is 1, and in that one also we find that the difference is 0. So we have exhausted all paths in our search, and therefore we conclude that these two functions are identical, right. But as you can see that the number of such paths can be very large, and so if we want to do it by this kind of combinatorial search, then for large circuits we are not going to get anywhere, right. So what we therefore do is we transform each circuit into a canonical representation. What is meant by a canonical representation? So the representation is going to be the same for a given function. So if I take 5 different implementations of that function, the canonical representation of all those 5 implementations will be only 1. Okay. So for a Boolean logic, the CNF is one canonical form, the conjunctive normal form is one canonical form, DNF is another canonical form, but we know that CNF and DNF can be very large, right. So if you enumerate all the min terms, then that can be again of the order of the size of the truth table. So that is not a smart thing to do. Question is, can we have a canonical form which is smaller than those, and that is what is answered by the BDDs. BDDs are canonical representations of the circuits for which are not typically not as large as the truth table. Okay. So, to understand what a BDD is, we first look at what is a decision tree. So, a decision tree is one where we for every variable, so for x1, if it is false we go this way, if it is true we go this way, and then after checking x1 we check x2, if it is false we go this way, if it true get this way, right. So, each path of this decision tree represents one valuation of the variables. So, if we take for example, if we take this path, then it represents the valuation x1 is 1, x2 is 0 and x3 is 0, and this node represents the function value. So, if x1 is 1, x2 is 0, x3 is 0, then the function value is 0. Now, you see this is like the truth table only, because every row of the truth table corresponding to that we have some node here. So, one path here. So, 0 0 0 is this path and the function value is this 0. Okay. Then when I look at 0 0 1, it is this path and the function value is 0, okay, and so on, right. So, this is a directed acyclic graph representation of Boolean functions. Now, what we are going to do is, we are going to see how we can construct a binary decision diagram out of this. Okay. So, in a binary decision diagram also, for every non-terminal vertex we have two arcs. One is called the low arc, which is going to be represented by a dotted line, and we will have a high arc which is going to be represented by a solid line. Okay. Each terminal vertex is labeled as 0 or 1. Okay. Now, let us, so what effectively is happening is that given a function f, we are first using a Shannon's expansion of this. What is a Shannon's expansion? If x is a variable in f, then I can decompose f by rewriting it as this, where fx is the function f where x has been substituted by 1 and fx dash is the function where x has been substituted by 0. So, this says that x is 1 and this is the function fx plus, which means or, x dash, and where the x has been substituted by 0. Okay. So, in a BDD, when you have a x node and if f represents this function, then this is represented by fx dash, this is represented by fx. Remember that the solid edge corresponds to x equal to 1 and the dotted edge corresponds to x equal to 0, right. So, if you have a BDD here, if you have a tree here, that tree represents the function fx dash. If you have a tree here, that represents the function fx. Okay. Now, there is the notion of ordering of the variables. So, in a ordered binary decision diagram, along each path the variables must appear in the same order. So, this is not permitted. So, here what is happening is, in this path we have x3 preceding x1, in this part we have x3 succeeding x1, right. So, this is not admissible. In every path they must follow the variables must come in the same order. Okay. Now, from a decision tree we are going to use certain reduction rules to get to the BDD. The first reduction rule is that we will merge equivalent leaves, right. So, the equivalent leaves are these, that these 3 and this one, they are equivalent leaves, sorry, this one also. So we will merge all of these, and the ones will also be merged. So there are 2 leaf nodes now, right? This is reduction rule 1. All right. So if you have 2 links to 0, we just bring them together. Reduction rule 2, we will merge isomorphic nodes. Now see here, let us look at this x3 and this nodes, these 2 nodes. We claim that these 2 nodes represent the same function. Why? Because what does this node represent? When x3 is 0, we go to 0, when x3 is 1, we go to 1. So what is this function? No, what is this function in terms of x3? x3 only. And what is this one? Also x3, right? So these 2 are the same function. So why do we have separate nodes for this? What we could do is we merge these 2 nodes, right? We merge these 2 nodes. So these 2 nodes are merged into this one node here, right? Because it's the same function. So now both of the 0 and 1 edge for this node is pointing to this, right? So we have merged these 2. Can we merge these 2? We cannot merge these 2, right? Because this one is going to 0 for both 0 and 1. We will remove it. But this one again is identical to this. So we can merge this one also with this, right? So these 3 nodes get merged into this one. This node remains independently like this. Okay. The rule is very simple. If you have 2 nodes, okay, if you have 2 nodes where the 0 edge is leading to the same vertex and the 1 edge is leading to the same vertex, what do these vertices represent? These vertices represent subfunctions. So this z vertex here represents some subfunction. So there is some BDD below this, and this vertex represents some function, let us call it g, okay, and this vertex represents some function, let us call it h, right. So this x is this f is x bar h plus xg, right. What is this function? If I call this function q, this is also x bar h and xg. So they are the same function, right. So what we should merge these 2 nodes. The function f and the function q are the same. They are both equal to x bar h plus xg. So we should merge these 2. That's what this says, that if your 0 edges are leading to the same vertex and the 1 edges are leading to the same vertex, then you should merge these 2 functions, these 2 vertices, because they represent the same function. Okay. Now this is what is happening with these 3 vertices. You see, for their 0 edges are going to 0 and the 1 edges are going to 1 for all 3 of them. Say all 3 of them represent the same function. Okay. So we merge all of these 3 and make their parents to point to the single merged node. So you see this edge out here is this edge. It is pointing to this node. Okay. This edge is here and this edge is here. they are all pointing to the same node now. Okay. But this one cannot be merged with this, right. And another thing that you must have seen is that we cannot merge nodes which have different variable names, obviously, right, that cannot be done. Is this clear how we merge this? So, we are basically in the whole BDD, if there are two nodes which are isomorphic in the sense that their 0 edges point to the same vertex, one edge point to the same vertex, then we can merge those two nodes because they actually represent the same function, right. So, this is what is being done. If they are the same node, then we merge these two into one node, make their parents point to the one node, and then remove this node, right. This node can now be taken away, not needed anymore. Okay. Now, next thing is the reduction rule 3. We can eliminate redundant vertices. So, vertices where the 0 edge and 1 edge point to the same thing can be eliminated. Why? Suppose this represents the function g, okay. Then what does this function f represent? This function f, what does it represent? It represents f is equal to x2 times g plus x2 bar times g, and what does it happen? You take g common, x2 plus x2 bar, so this is effectively equal to g itself, right. So, rather than making this edge point to this node, we could actually redirect this edge to this, and this node becomes superfluous, right. So, see, that is exactly what we have done. We have taken out this node and made it directly point to this. Similarly, this one is a redundant node, so we take this edge and point it to here, okay, this. Okay. So, in the generic sense, what we are doing is if both edges are pointing to the same node, then we just remove that node, we just get rid of this one, alright. Is this clear, the three rules, right? With these three rules, the BDD is reduced, okay, and there are some other tricks which we are not going to talk about, like how negations are used. If you have a BDD, if you have a function and if you have its negation, then rather than creating a BDD for the negated function, you can put a special type of edge which you call as a negated edge, right. So, it is like when you draw a circuit with NOT gates which has NOTs, you sometimes use a bubble just before the input of another gate, right. So, instead of say when you want to write instead of writing this, okay, we sometimes just do this, right. So, in the BDD also there is a nice optimization which is done, is that if you have the BDD for a function f, right, which is maybe for some variable it is connected to this, and then somewhere in the BDD you need f bar, then instead of creating another BDD for f bar, you can point that to this using a negated edge. So, it is a edge which has a special characteristic, it is a sign, okay, that whether it is a positive edge or a negative edge. This leads to significant amount of reduction in the size of the BDD. So, BDD packages regularly use that, but let us not get into that. Mainly these three reduction rules that we talked about are the three reduction rules that are used to reduce the size of the BDD. So, if you look at this example, this was the initial decision tree, and after the reduction this is what you get, okay. So, much lesser than the original side, okay. and this for a given variable ordering. Remember, this is ordered BDD and then reduced. Okay. For a given ordering of the variables, the BDD is canonical, right. So, no matter what is the original function from where you started, after you have reduced it for that ordering, you are going to get the same graph. Alright. This is the good property of the BDD. So, because it is canonical, for the same variable ordering, two functions are equivalent if and only if their graphs are isomorphic, right. How does the BDD how do you check for isomorphism in the BDD? If there is a function f, now let us see, I have given you two circuits, okay. One circuit is for some function a f given the inputs I1 through Ik, okay. I give you another circuit which takes the inputs, same inputs I1 through Ik and produces a function g. I want to determine whether f and g are equivalent, right. So, what I do is I create a BDD for f. What are the variables that are there in this BDD? These inputs I1 through Ik. I create a variable another for g, I1 through Ik. How do I test their equivalence? These two should be isomorphic. Now, suppose they are using the same structure. Now, suppose you think of this as the same BDD. See, the BDDs are going to share it, all common functions will be shared, right. So, when you reduce these two BDDs together, what will happen? If they are the same function, f and g are going to point to the same node. Is that clear? They will point to the same node, because reduction is going to make, or it is going to take the functions in common, right. The whole of the thing will come in common, and in the BDD you will see the function f and the function g are pointing to the same node, right. Then you know that they are equivalent, right. Now, let us see some the BDDs for some typical functions like x1 or x2 and x4. This is a BDD for that, right. So, you see that if x1 is high and x4 is high, then we take this path, right, x1 x4, then it is 1. If x1 is low, x2 is high and x4 is high, then also it is 1, and it is 0 when all three are 0, right, or any two of if x1 x2 are both 0, then this becomes 0, so it goes to 0 and so on. This is a circuit for, this is a BDD for odd parity, right. So, the function will be 1 when you have odd parity. So, if only x1 is 1 and all three are 0, then it is 1. If x1 is 1, x2 is 1 and the remaining two are 0, then it will become 0 because it is even. So, you can see that if you take an odd number of red edges, then you come to 1. If you take an even number of red edges, then you end up with 0. So, this is an example. So, for a 4-bit adder, and this is the corresponding BDD. Okay. Now, see what is happening here is that this has 5 outputs, the 4 sum bits and the carry out, right. Now, in this BDD, see the BDD does not create 4 different BDDs for S0, S1, S2, S3 C out, right. They are all created under the same BDD and they share functions. See, that is the smart thing to do, right. If you have a multi output function, then you put them all on the same BDD so that they can share as much of the sub functions as possible, right. So, for example, see, this node represents S0, but that is being used by the BDD for S1, and the BDD for S1 is being used by the BDD for carry out. In fact, carry out is going to use all of these, I think, right. So, that is the thing. Now, in a BDD package, you get a set of functions. So, your variables can be declared at the beginning. You can define the ordering of the variables. So, A followed by B followed by Z followed by C, you can define the variable ordering, and then you can start building functions. So, if you have a BDD for function f and if you have a BDD for function g, you can call a BDD function to compute the AND of f and g, or the OR of f and g, okay, or the XOR of f and g. So, there is a BDD AND function, BDD OR function to compute that. We are going to see how those functions will work. It is going to give you the pointer to the function node which represents the AND of those two functions, but the BDDs for f and g are still there in that structure only. So, are you getting what I am saying? See, there is one structure that it is going to use, right. So, in that structure it is going to create the BDD for f. When you create the BDD for g, if that function uses some sub functions of f, then it will use that. So, the BDD for g is not necessarily a completely separate thing. It might use certain common sub functions represented by these nodes. These are part of f, these are part of g, and then when you do f and g, okay, it is going to build the f and g using these and return you some node. So, this was your f, this was your g, it is going to give you some node corresponding to f and g, but these are also there in the same thing. So, you have a notion of a BDD manager. The BDD manager is the data structure for this whole thing, and then for each of these BDD functions you can have one BDD, right. So, remember that you can have several pointers into this structure. Each pointer represents a different function, right, and the whole data structure is a shared data structure among all these functions, right. If you want it to be a completely separate BDD, then you take another BDD manager and then start with that, right. This is how a BDD package can be used. So, here you see that all this is sharing all these sub functions for creating the BDDs for S0, S1, S2, S3 and C out. Now, variable ordering has an effect on the performance of the BDD packages. So, suppose we look at this function A1 and B1 or A2 and B2 or A3 and B3. Now, one ordering for this is A1 less than B1 less than A2 less than, so it is in this order. What does this mean? That in the BDD, in every path of the BDD, the variables will come in this order, right, and this is another ordering where A1 then A2 then A3 then B1 then B2 then B3. The BDD corresponding to this one, this ordering is this. The BDD corresponding to this one is this. Now, you see this one has many more nodes, right. Now, intuitively for this example, you see that what we are doing here is we are taking A1 and B1 So this part represents A1 and B1. So if A1 and B1 are both 1, then because this is OR, so this side gets resolved to 1 straight away, right, and this side is looking at this remaining function. Okay. So it is like I call this as F and this as G, right. So I have the BDD for F here and then the BDD for G here, and then if this part is true, if this part is false, only then I go to this part. If F is false, that is represented by these two green edges, then I go to G. So this is my G, okay, this is a G, and then within G again I have this part which I call as H, right. So this represents H, right. So G is this part, H is this part. So since one side is going away for each of these ORs, the one side, so it is not combinatorially blowing up. On the other hand, you see, if I tell you the values of A1, A2 and A3, you will not be able to decide the value of the function except for the case where all three are 0. Except for the case where all three are 0, you will not be able to decide the function value if I give you the values of A1, A2, A3. So there is a combinatorial growth here in this part, right. So this is what is making the size larger, and then it is shrinking once the values of the B's become available, right. So typically a BDD is going to look like, it is going to have a barrel shape, right. It is going to have a barrel shape. Initially when you are not being able to decide the value of the function, you are opening it up like a tree, and then once your decisions start coming in, the BDD starts shrinking, and at the end again it goes down to only 2 nodes, 0 and 1, right. So it is a barrel shape. We do not want the barrel shape, we want it like a cylinder, right, because barrel shape means it is growing, the BDD size will grow up. Now all functions are not amenable for this kind of thing, they will not yield a linear kind of structure for the BDDs regardless of your ordering, right. But here you see that a good ordering can save a lot number of nodes. So the immediate question is, how difficult is it to find a good ordering? And the bad news is that finding out a good ordering is an NP complete problem, right. Finding out whether you can improve the ordering is NP complete, right. See, please remember that underlying this construction of BDDs there is a SAT, because what is the BDD corresponding to an unsatisfiable function? How is it going to look like? How is the BDD for an unsatisfiable function going to look like? Everything will collapse to 0. So the BDD corresponding to an unsatisfiable function is this, and the BDD corresponding to a valid function is this. This has no minterms, this has all the minterms. So you see, it is not fair to expect that if the number of minterms grow, the BDD size will grow, right. It will grow, but then it is going to shrink once again, and in the end when you have all the minterms, it has shrunk to 1 node, right. Okay. Now see, if you are able to construct the BDD, you can immediately say whether the function is satisfiable or unsatisfiable, right. SAT is NP complete, so the hope of being able to build the BDD in polynomial time is gone, right, because it is also NP complete. If we could build the BDD in polynomial time, we could check whether it is a 0 node only or a 1 node only and say whether it is justifiable or unsatisfiable. The other important thing from a theoretical point of view for computer scientists is, you see, the satisfiability problem is in NP, the validity problem is in co-NP, right. What is a problem in NP? Where you can take the decision non-deterministically in polynomial time and verify whether the answer is yes in polynomial time. If the answer is no for a problem in NP, you do not have a polynomial time verification procedure, at least known polynomial time verification procedure is not there. For a problem in co-NP, the no answer can be verified in polynomial time, the yes answer cannot be verified. So, if I give you a formula and say is it satisfiable, and I give you an instance and say that look it is satisfiable, you substitute those variable values and check whether it is satisfiable in polynomial time. But if I tell you this is unsatisfiable, how will you verify whether I am bluffing or not? There is no way you can verify whether I am bluffing or not, right. On the other hand, think of the validity problem. If I say that it is not valid, then I can give you a counter example. I can give you an assignment for which the function evaluates to 0 and say that look it is not valid. But if I say that it is valid, how will you verify that I am correct or not, right. So, the first problem SAT is in NP, the validity problem is in co-NP. If you have the BDD, you can answer both. You can say whether it is satisfiable, you can say whether it is valid, right. So, that is a nice property of this, and so we are spending time in building the BDD, but once we have the BDD you can answer a lot of questions, right. And getting a good ordering, as we saw, is an NP complete problem, right, because if we could do that, then for a whole lot of problems we could solve the SAT in a much better way, right. Now, there are a lot of heuristics which select a good variable ordering, right, and one can study those heuristics, and the BDD packages use scores of heuristics to keep the size down. One of the concepts which has become very popular and is supported by every BDD package is called dynamic variable ordering. So, this was introduced by Radel in a paper in ICCAD in 93. What it does is it says that look, when you are using the BDD, when you are building the BDD, I can incrementally swap the ordering between variables to improve the size of the BDD. So, what I do is I take two variables, say which are succeeding each other in the variable ordering, and I just say that let me put this ahead of the ordering and let me bring this down in the ordering. So, I had x and y, x was preceding y in the ordering. So, I now say that let y come first and x come later, right. So, just swap immediately successive layers of the BDD, right, and he gave a nice procedure for doing that without having to do it traverse the entire BDD, right. So, you just make local changes and affect that, and that has turned out to be a very useful heuristic, and it continuously the BDD manager does dynamic variable reordering. It is a greedy approach. You do it when it reduces, right, and see whether it reduces. If it reduces, then apply that step, but the greedy approach usually works out pretty nicely, and it is able to bring down the size of the BDD significantly. So, when you see in a BDD package, when you start using the BDD package, the size of the BDD starts growing, okay. Now, when it reaches the size of the memory in your system, at that time it gets stretched for memory. So then it is going to spend a lot of time doing this reordering. So you will see that it is taking a lot of time to build the next BDD, because it is going to do a lot of reordering, bring the size down and then do the next operation. Otherwise it will run out of memory for doing the next operation. So the idea, as I said, is just this, that you swap two layers. So here you had B1 and then B2, you just swap the two layers and bring B2 up and B1 lower, and then do further reductions to see whether the size goes down. So here it is again doing another level of reordering with B3 and B1, right, and then tries to, so see, I have not shown any reduction here. What I am saying is just the concept, that the way in which it is going to do that, okay. And then it can again, you know, do this until maybe B1 goes right up there, and then maybe takes B1 right at the top. It is just a this thing, and then you see that this is possibly the best choice for the function, right. Now the nature of BDDs for different functions have been studied. So for ALUs like adders and subtractors, etc., we find that the best size of the BDD is linear and the worst is exponential. So ordering sensitivity is high. So if you get a good ordering, then you are going to get a linear size BDD. If you do a bad ordering, you will get an exponential size BDD, right. For symmetric functions, the best is linear and the worst is quadratic, right. So the ordering sensitivity is low, right. There is no ordering sensitivity actually. For multiplication, the best one is exponential, the worst one is also exponential. So this is a class of functions for which BDDs really take a good beating actually, and the ordering sensitivity is low, because it does not matter what way you order it, you are going to get a bad BDD, right. So for taking care of multiplication, people have adopted other types of decision diagrams, which we shall see in due course of time. Many tasks have reasonable OBDD representations. Algorithms remain practical for up to something like 100,000 node OBDDs, and much larger these days actually, because these continuously keep evolving. Now what we are going to do in the next few slides is, we are going to study how BDD operations take place. So when we say that we are going to take the AND of two functions, how does it internally happen inside the BDD, okay. Then we are going to look at the algorithmic properties. The arguments are OBDDs with identical variable orderings, result is an OBDD with the same ordering, and we are going to look at a closure property, okay. Now I do not think we are going to go into an actual operation here in this class, we are going to take it up in the next lecture, but let us at least see what is the general philosophy of doing this. So when you are in one node and you want to do f operation some g, okay, then what we are going to do is, we are going to do x dash of this and this, okay. So we are going to follow the Shannon's expansion. So let me see what we mean by that. So suppose I have a BDD for f, so this is some BDD here, and then this is the one edge, okay, and I have g, okay. Now I want to do f of g, where op can be AND or XOR, whatever, right. Now let us call these functions let us say h1, say h0, h1, and let us call this q0, q1. These are these functions, not the variables, mind you, right? Now, suppose that both of these are x, the variable is x, right? Then I can write this as when x is 1, right, then h1 of right, okay, that is what this means, or x bar and h0 right. How did I get this? Because I can write f as xh1 plus x bar h0. I can write g as x q1 plus x bar q0, right. Now, when you do f of g, then it is this one of g is xh1 x dash h0 of xq1 plus x bar q0, right. And now, since these are complementary, so I can reduce that to this, right. Now, did you notice one very interesting thing here? We did all this without care for what op is. We have never used what op is here. We have performed this operation, we have reduced it to h1 op q1 and h0 op q0 without considering what op is. Now, that is a very interesting thing. So, your procedure for this apply operation is not using that right now. Where is it that going to be useful? When we go down to the 1 and 0, when h1 is 1, q1 is 0, that is where the op will be used, right. See, so the entire traversal of the apply operation can take place without considering what operation. So, it is the same for any operation. It is only at the leaf level that the actual operation is being applied, actual operator is being applied. So, that means you see, you can write a very generic procedure for doing this, which is not going to be different whether op is an AND or XOR whatever, okay. So, in the next class we are going to look at this apply operation, right, and then see how it performs.